Okay, let's jump right into this explainer. Today we're taking a close look at how battery energy storage systems, which are absolutely crucial for our modern power grid, are facing their ultimate test against extreme weather. Just picture it, a pristine, containerized battery system sitting right in the middle of a massive industrial test facility. It's surrounded by high-tech thermal cameras, heavy-duty sensors, and structural monitors. We're going to explore what happens when this vital technology is put through a rigorous, almost cinematic fire and ice safety test to see exactly how it handles the absolute extremes of our changing climate.
Now, what's really fascinating about that scenario is that it exposes the single greatest vulnerability of these multi-million-dollar installations. They are incredibly temperature sensitive. As we start deploying these massive battery farms into much harsher environments, we're talking everything from blistering desert heat waves to freezing Arctic snowstorms. We're actively pushing the limits of conventional battery architecture. You see, the very chemical reactions that allow us to store and dispatch energy are the exact same reactions that can become unstable or completely degrade the moment the environment turns hostile.
Let's kick things off with Section 1, the climate crucible.
So, extreme temperatures go right after a system's usable capacity, its performance, and its physical safety. When you track capacity loss over time, the financial hit is undeniable. As temperatures constantly fluctuate, the battery's degradation accelerates rapidly. Extreme heat actually speeds up these unwanted side reactions inside the lithium-ion cells, while extreme cold limits charging and slashes the usable capacity. But the real kicker? Uneven temperatures cause cells sitting right next to each other in the exact same module to age at completely different rates. That directly kills a project's long-term return on investment, forcing premature equipment replacements and crippling reliability right when the grid needs power the most.
Moving right along to Section 2, ice, the cryogenic threat.
What actually happens when we drop our test chamber way below freezing? Well, the complex chemistry inside the battery shifts, and it gets dangerous. Repeated freeze-thaw cycles create these twisted, tortuous paths for the electrolyte to literally seep out into the environment. As the system freezes, ice formation actually restructures how chemicals move around inside. So, while a frozen layer of ground might seem like it would stop leaks from going straight down, it actually generates these highly conductive, unfrozen brine channels. And those channels force toxic electrolytes to spread outward laterally, creating really dangerous, concentrated pollution hotspots. And the physical failure mechanisms at sub-zero temperatures are just massive threats to structural integrity. The organic electrolytes experience severe thickness surges, and physical components literally begin to freeze and snap. Below -20 degrees Celsius, the fluorinated rubber seals completely lose their elasticity, causing microcracks, and at -15 degrees, the aluminum current collectors go through this wild transition where they become about as brittle as dry pasta. Obviously, that dramatically heightens the risk of an internal short circuit.
Now let's flip the thermometer entirely for Section 3, fire and thermal runaway risks.
If we crank up the extreme radiant heat in our test environment, we quickly approach a terrifying threshold, thermal runaway. What happens is, localized hotspots age the battery cells unevenly and push the entire system to the brink. If the cooling systems can't dump that heat fast enough, a single failing cell heats up its neighbors in a cascading chain reaction. Once internal temperatures hit that 120 to 150 degrees Celsius mark, the chemical reactions become entirely self-sustaining. Heat builds up way faster than it can possibly be removed.
And once that thermal runaway starts, the system faces hazardous off-gassing and the potential for a catastrophic explosion if it's not managed perfectly. The extreme heat breaks down the electrolyte molecules, generating highly toxic hydrogen fluoride gas. So it's not just a fire hazard anymore, it's a severe chemical and explosion threat. The thick metal enclosure can deform, venting heavy black smoke and pushing the entire safety architecture to its absolute physical breaking point.
So how do we fight back against these extremes? That brings us to Section 4, Defense Level 1, Regulation. The industry uses a defense-in-depth strategy, and it starts with strict rules. Pre-2018, systems were honestly pretty loosely integrated, but the 2026 NFPA 855 updates are a massive game-changer. They shift the burden squarely onto the manufacturers, demanding rigorous, large-scale UL 9540A fire testing. Basically, manufacturers have to intentionally ignite their own systems in a controlled test lab just to physically prove the equipment can survive thermal runaway, and to document exactly how gas composition and explosion controls perform under pressure. This compliance ensures that safety isn't just an afterthought anymore. You can't just treat these massive batteries like standard electrical rooms. The 2026 standard literally mandates a 20-meter outdoor safety buffer from any important buildings, alongside heavily coordinated detection and suppression networks. Facility managers have to proactively build out pre-incident plans. And why does this matter so much? Because it's not just about passing bureaucratic red tape. It's fundamentally about preserving human life and ensuring everyone knows exactly what they're dealing with before an emergency actually strikes.
Moving to Section 5, Defense Level 2, Response.
If all those design precautions fail, the second layer of defense kicks in, relying on first responders to execute a highly tactical action plan. Responders have to methodically work through these steps, treating the situation with extreme caution. We're talking severe risks of electric shock and latent reignition. Because these fires involve complex, dangerous chemistries and energized metal boxes, crews usually operate in full protective gear, using thermal imaging cameras from a very safe distance, prioritizing external containment above all else.
1,900. That is the bare minimum number of liters of water per minute that an external hydrant has to supply for at least 2 solid hours to properly control a BESS fire. To put that into perspective for you, that is like emptying a large hot tub directly onto the fire every single minute. This massive water requirement just highlights how insanely intense and stubborn these chemical fires are. Without that sustained, huge volume of water, cooling the core down enough to stop it from just reigniting again is practically impossible.
Finally, we reach Section 6, Defense Level 3, Engineering.
This is the most proactive layer of defense. It's about stopping temperature gradients at the source, preventing fires and freezing damage before they can even start. Conventional HVAC or cold plate systems only remove heat indirectly. That leaves physical thermal gaps and creates uneven temperature zones across the battery pack. But immersion cooling technologies, like Liquid Shield, take a totally different approach. They submerge every single cell directly into a dielectric fluid. It touches every exposed surface, giving you perfectly uniform thermal control.
By stopping an ignition event right at the chemical level, immersion cooling acts as the ultimate physical safeguard against both freezing damage and thermal runaway. Think about it. If a cell fails, the surrounding liquid instantly isolates it from oxygen, so the flame is suppressed immediately. Plus, because it distributes heat so evenly during both massive hot and cold spikes, testing shows it can actually extend the overall battery life by up to 20% compared to cold plates. It's a complete paradigm shift, moving from reacting to a fire to physically making it impossible for one to start.
Which leaves us with a pretty provocative final thought to wrap up this explainer. As extreme weather becomes the new normal, investing in these multi-layered defenses isn't just about passing a safety test anymore. It's about securing the future of our entire global power grid. Whether we're enforcing rigorous NFPA standards, properly equipping our first responders, or deploying cutting-edge engineering like immersion cooling, building deep resilience into our energy storage is no longer optional. It is absolutely the mandatory baseline for a stable future.